Hey there, friend. Take a breath and let the day fade. Tonight, we'll quietly explore how quantum physics touches your everyday life, from your screen to your memories to time itself. Get cozy and let's begin. Chapter 1. The Quantum World Beneath Your Life, an Introduction. You may not see it, feel it, or consciously perceive it, but beneath everything you do, every breath you take, every message you send, every pixel glowing softly on your screen, there is a hidden world governed by laws so unintuitive, so delicately strange that they defy common sense. This world is the quantum realm, and though it operates on scales so small they defy ordinary vision, its consequences ripple outward to shape the technology, medicine, communication, and structure of modern life. Quantum physics, or quantum mechanics, is the scientific framework that describes how particles like electrons, photons, and atoms behave. It is not merely a different set of rules. It is a radical departure from the certainties of classical physics. While classical physics gives us the tools to predict the movement of a thrown baseball or the path of a planet, quantum mechanics addresses phenomena on the atomic and subatomic levels, where particles don't seem to obey ordinary expectations. Instead, they flicker between possibilities, behave like waves and particles at once, and remain fundamentally probabilistic. At the heart of this framework lies an essential truth. The universe behaves differently when you look closely. If classical physics is a clockwork of predictable gears and wheels, quantum physics is a shimmering web of probabilities. It's not that things don't happen with precision, but rather that the precision lies in statistical predictions, not deterministic outcomes. Electrons don't orbit nuclei like planets around the sun. They exist in a cloud of probability where their exact position cannot be known, only the likelihood of where they might be found. This is not a statement of technological limitation, but a fundamental property of reality described by Heisenberg's uncertainty principle. The famous double-slit experiment illustrates this paradox perfectly. When particles like electrons are fired through two slits and left unobserved, they create an interference pattern on the other side, a hallmark of wave behavior. But when scientists try to measure which slit each electron passes through, the interference pattern disappears and the particles behave like classical objects. The act of measurement collapses the wave of probabilities into a single outcome. Observation changes reality. This strange interplay between potential and actuality lies at the foundation of quantum mechanics. While these phenomena might seem distant from daily experience, they are not. In fact, they are the reason modern electronics exist. The transistor, which forms the core of every modern computing device, operates through the quantum behavior of semiconductors. These materials allow electrons to move in controlled ways by manipulating energy bands and barriers. Electrons can tunnel through barriers that they shouldn't be able to cross according to classical physics, an effect known as quantum tunneling. This is not a flaw, it's a feature that engineers use to build smaller, faster, and more efficient devices. The rules of the quantum world also dictate the behavior of light-emitting diodes, or LEDs, where electrons jump between energy levels within a material and emit photons of specific wavelengths, creating visible light. This precise quantization of energy ensures that every color of light has a predictable energy, frequency, and application. From display screens to data transmission through fiber optics, quantum physics is in every pixel and pulse. Even the simple concept of heat is underpinned by quantum rules. When objects are heated, their atoms vibrate more rapidly. But at a fundamental level, these vibrations occur in quantized units called phonons. In solids, thermal conductivity, how well a material conducts heat, is a quantum mechanical process involving the movement of phonons through a lattice of atoms. Without quantum mechanics, our understanding of temperature, conductivity, and resistance would be incomplete. Quantum mechanics also underlies the principles of magnetism. The magnet on your refrigerator clings to metal because of the collective alignment of electron spins, a property that is purely quantum in nature. Spin is not a rotation in space, but an intrinsic form of angular momentum that particles possess. It's quantized, meaning it only comes in discrete values, and it governs how electrons fill atomic orbitals and how they interact with magnetic fields. The physics of materials, why metals conduct electricity, why insulators resist it, and why superconductors can carry current with zero resistance, is also entirely quantum. When electrons move through a conductor, they do not flow like water through a pipe. Instead, they exist in states defined by the quantum properties of the material. These properties determine how easily electrons can jump from one energy band to another, and whether or not they encounter resistance along the way. One of the most precise applications of quantum mechanics in modern life is timekeeping. Atomic clocks, which define the standard for time used in GPS, telecommunications, and scientific research, rely on the resonance frequencies of atoms, typically cesium or rubidium. These frequencies are defined by transitions between quantum energy levels in the atoms, and they are so consistent that atomic clocks lose less than a second over millions of years. The position data from GPS satellites, for instance, would drift by kilometers each day if not for the quantum precision of the clocks they carry. In the world of medicine, quantum mechanics quietly saves lives. Magnetic resonance imaging, or MRI, is based on the quantum property of spin in hydrogen nuclei. When exposed to a magnetic field, these nuclei align and can be flipped using radio waves. The signals they emit as they relax back to alignment provide highly detailed images of soft tissue, allowing doctors to detect tumors, injuries, and neurological conditions with extraordinary clarity. Without the quantum behavior of atoms, this diagnostic window into the body would not exist. Even the chemistry that governs biological life arises from quantum rules. The shape and reactivity of molecules depend on how electrons are arranged in orbitals, which are regions of probability defined by the Schrödinger equation. Bond formation, enzymatic activity, and even the way DNA stores and replicates information, these are all dictated by the subtle interplay of quantum energies and electron behaviors. Life, in all its complexity, is an emergent property of quantum interactions. Quantum mechanics is also shaping the frontier of computing and communication. The development of quantum computers, which use qubits rather than classical bits, promises to solve certain problems far more efficiently than traditional computers. These include simulating molecular interactions for drug discovery, optimizing complex systems, and performing cryptographic analysis. While today's quantum computers are limited in scale and stability, their trajectory suggests a radical transformation in how we harness information. The emerging field of quantum communication leverages quantum entanglement and uncertainty to create secure communication channels. In quantum key distribution, encryption keys are shared through quantum states of photons. Any attempt to intercept or measure these states alters them, alerting the system to a breach. This approach could render data transmission theoretically immune to eavesdropping, providing an unprecedented level of security in finance, defense, and personal communication. The entanglement phenomenon, once dismissed by Einstein as spooky action at a distance, has been repeatedly verified. It shows that particles can remain correlated in ways that defy local realism. If you measure one entangled particle, the state of its partner becomes defined instantly, regardless of the distance between them. Though no usable information travels faster than light, the mere fact that such correlations exist challenges our conventional understanding of separability and space. And then there are quantum sensors, devices designed to measure with astonishing sensitivity. They can detect the tiniest shifts in gravitational fields, minute changes in magnetic environments, and even the presence of individual molecules. These tools are revolutionizing fields from neuroscience to geology, allowing us to map the brain in real time or detect underground structures without digging a single hole. Quantum mechanics is often portrayed as a domain of the strange and abstract, but in truth, it is the most empirically successful theory in the history of science. Every test of its predictions has matched observation. Its equations guide the design of everything from microwave ovens to particle accelerators. And its implications continue to unfold in both technological innovations and philosophical inquiry. You don't have to understand every equation to feel its reach. The lights above you, the phone in your hand, the GPS guiding your steps, all of these depend on particles obeying quantum rules. Even the chemistry of your thoughts, the firing of neurons, the dance of calcium ions across synapses, happens in a world governed by probabilities, uncertainty, and interactions that only quantum physics can describe. And perhaps, in the quiet of the evening, when the noise of the day fades and your thoughts drift freely, you may pause and realize that the universe is far more mysterious than it first appears. That beneath the solidity of things, there is only vibration, fluctuation, and probability. You are not separate from this world. You are a ripple in its quantum field, a temporary arrangement of energy and form. In the silence beneath it all, you are the quantum world, experiencing itself. Chapter 2. How Quantum Mechanics Powers Your Smartphone. Your smartphone, a slender object that fits in the palm of your hand, is one of the most advanced technological artifacts ever created. It sends and receives signals from satellites orbiting thousands of kilometers above. It processes images, encodes speech into data, streams videos across continents, and even responds to your voice with near-human fluency. But what is rarely considered is that its most vital inner workings rely not on gears or wheels, nor on the predictable laws of classical mechanics, but on the probabilistic, abstract, and often invisible rules of quantum mechanics. At the core of every smartphone is a processor, an integrated circuit composed of billions of transistors etched into silicon. These transistors are the fundamental switching units that allow your device to perform logic operations and store information. A transistor can be thought of as a tiny electronic gate. It controls whether current can pass through a particular pathway in the circuit. In digital logic, this is interpreted as a binary value, on for 1 and off for 0. Yet at scales this small, tens of nanometers, electrons do not behave like tiny billiard balls flowing through pipes. Instead, they exhibit wave-like properties. They can tunnel through barriers, interfere with themselves, and distribute their location across a cloud of probabilities. Classical physics breaks down at these scales, and engineers must rely on quantum models to predict and control the behavior of current in these circuits. The very notion of switching in a modern transistor is governed by the likelihood of electron tunneling across a potential barrier, a purely quantum phenomenon. The materials used in these circuits are also chosen and engineered based on their quantum mechanical properties. Silicon is a semiconductor, which means it has electrical properties that can be finely tuned by introducing small quantities of other elements, a process called doping. When doped with phosphorus, silicon becomes rich in free electrons, creating an N-type material. When doped with boron, it develops holes, places where an electron is absent, creating a P-type material. The interface between these two types of silicon creates a junction that behaves in precisely predictable quantum ways, allowing the control of charge flow in circuits. Semiconductor physics is deeply rooted in quantum band theory. This theory explains how electrons occupy energy bands and how these bands determine whether a material is a conductor, an insulator, or a semiconductor. In conductors, the valence band and conduction band overlap, allowing electrons to flow freely. In insulators, a wide gap separates these bands, preventing electron movement. In semiconductors, the gap is narrow enough that electrons can be excited, either thermally or by an electric field, into the conduction band, where they become mobile and can contribute to current. Quantum mechanics also explains how these electrons interact with lattice vibrations, bonons, which can cause scattering, resistance, and thermal effects. Engineers must account for these interactions to design chips that not only work efficiently, but also manage heat dissipation. As circuits become smaller and more densely packed, quantum effects like leakage current, where electrons tunnel through thin insulating barriers, become increasingly pronounced. Far from being a nuisance, these effects must be embraced and managed through precise quantum modeling, material science, and fabrication techniques. The screen on your smartphone is another place where quantum physics quietly enables functionality. Whether it's an OLED or LED backlit LCD display, the creation of light involves quantum transitions. In OLEDs, organic molecules emit light when electrons and holes recombine, releasing energy in the form of photons. The color of the light depends on the energy gap between quantum levels in the material. Every hue and shade on your screen arises from a controlled quantum event. The design of these molecules is not a matter of trial and error. It involves calculating electron energy levels using quantum chemistry and tailoring the molecular structure to emit precise wavelengths. Touchscreens, too, depend on quantum principles. Capacitive touchscreens detect the electrical field distortion caused by a human finger, which is conductive. The fine metal grids that sense this distortion are designed to detect extremely small changes in capacitance. The conductivity of these materials and their response to electrical fields depend on the quantum structure of their electron shells and how they interact with the crystal lattice. Quantum effects are also embedded in your phone's memory. Flash storage relies on floating gate transistors, which trap electrons to represent a stored bit of data. Electrons are moved to and from this floating gate by quantum tunneling, a process where particles pass through energy barriers that would be impenetrable according to classical physics. The reliability and speed of flash memory are direct consequences of this finely controlled quantum effect. Beyond hardware, quantum physics plays an important role in how your smartphone communicates. Wireless signals, such as those used in 4G, 5G, Wi-Fi, and Bluetooth, rely on the generation and detection of electromagnetic waves, which are composed of photons, quantum particles of light. Radio antennas transmit and receive these waves, but the conversion of signal to data and back again requires the use of precise electronic filters and amplifiers built using quantum-designed semiconductors. Camera sensors in smartphones are made of photodiodes, usually built from silicon. When photons strike the sensor, they excite electrons from the valence band to the conduction band, generating an electric signal. The number of excited electrons corresponds to the light intensity, and this data is used to form an image. The quantization of light into photons and the photoelectric effect that enables their detection are both inherently quantum phenomena, first explained by Einstein in 1905. Even more abstractly, the software that runs on your smartphone has been written, compiled, and executed on machines whose function depends on quantum mechanics. The processors used in code compilation, the storage media used for data, and the transmission systems that move that software to your device all rely on the same quantum principles. When you browse the internet, you are relying on encryption algorithms that, while classical for now, are designed with quantum attacks in mind. The coming age of quantum computing is already influencing the software architecture of tomorrow's devices. There is also the quantum limit to consider, the threshold below which classical approximations no longer suffice. As smartphone components continue to shrink, approaching the atomic scale, quantum uncertainty becomes not a fringe factor but a dominant one. The The size of a single transistor is now measured in atoms. At this point, even the thickness of a gate oxide layer, a few nanometers, can no longer be treated as a static medium. Electrons see it as a finite potential barrier and may tunnel through it, causing leakage current. This leakage must be managed or it will overwhelm the circuit's function. Thus, the act of scaling down becomes a battle not of classical miniaturization, but of quantum control. Advanced smartphones now contain sensors for motion, proximity, and orientation, gyroscopes, accelerometers, and magnetometers. These devices often rely on microelectromechanical systems, MEMS, which in turn depend on quantum-level materials science to function reliably at small scales. As these sensors become more sensitive, future generations may incorporate quantum-enhanced versions using entangled particles or spintronic effects to increase precision. The field of spintronics, electronics that use the spin of electrons, not just their charge, promises new methods of data storage and logic. Magnetoresistive random access memory, MRAM, which uses spin-aligned electrons to encode bits, is one such example that already exists in high-performance applications. Your smartphone may one day include memory that leverages spintronics, increasing speed and durability while consuming less power. In coming years, quantum sensors could allow smartphones to detect their orientation and location with extraordinary accuracy, even without GPS. They could measure environmental conditions, atmospheric gases, or magnetic anomalies with precision that far exceeds current capabilities. These applications, once limited to laboratories, are gradually making their way into the commercial ecosystem. All of this is possible because long ago, physicists accepted the strange but undeniable behavior of the quantum world. They built models that didn't always make sense to the classical mind, but yielded predictions that aligned with observation. These models, refined over decades, were transformed by engineers into design rules, and then into working devices. At each stage, abstraction became implementation. What began as a theoretical insight became something you can hold in your hand. The fact that you can take a picture of the stars, video call someone on the other side of the planet, or listen to music composed centuries ago, all from a piece of silicon, glass, and metal no thicker than your palm, is a triumph not of mechanical engineering alone, but of quantum understanding. Your smartphone is not just a device. It is a cascade of quantum phenomena made real and usable, carefully designed by human minds to harness the abstract rules of a universe that, for the most part, remains invisible to us. And perhaps that is the most profound realization, that something as personal, as mundane, as familiar as your phone, something you carry with you, touch daily, trust with your memories, operates through rules that no one can see, that no one fully understands intuitively, and yet they work. That beneath every tap, every call, every connection, the universe is humming its quiet quantum tune, and you, unknowingly, are already fluent in its language. You are not merely using quantum technology. You are living within it. Chapter 3. Quantum rules inside every LED and laser. You live in a world illuminated by quantum events. Whether you're reading this on a smartphone, passing beneath traffic lights, watching a film in a cinema, or having a barcode scanned at a checkout counter, you're interacting with photons, packets of light energy, produced and controlled by deeply quantum mechanical processes. In particular, light-emitting diodes, LEDs, and lasers, two of the most common sources of artificial light in modern life, rely entirely on the precise behavior of electrons and energy levels as described by quantum physics. These are not classical light sources in any traditional sense. Their functionality arises from quantized electron transitions within atoms and engineered materials. Without quantum mechanics, neither LEDs nor lasers would function. In fact, the principles that power these technologies were among the earliest triumphs of quantum theory. To understand how an LED or laser works, one must begin by recognizing that atoms and semiconductors do not allow electrons to occupy just any energy. Instead, electrons exist in discrete energy levels. This idea, first hinted at by Planck and expanded by Bohr, eventually evolved into a full understanding of electron bands in materials. In semiconductors, the two most important energy levels are the valence band and the conduction band. The valence band is filled with electrons that are bound to atoms, while the conduction band contains electrons that are free to move throughout the material and contribute to current flow. Separating these bands is a forbidden energy gap, an energy range that electrons cannot occupy. For an electron to jump from the valence band to the conduction band, it must absorb energy equal to or greater than the size of the gap. Conversely, when an electron in the conduction band falls back into the valence band, it can release that energy, often in the form of a photon. This process, known as radiative recombination, is the foundation of how an LED works. In an LED, electrons are injected into a semiconductor material that has been engineered so that when these electrons recombine with holes in the valence band, they emit photons with energies corresponding to the material's band gap. The color of the light, whether red, green, blue, or any other, depends on the energy difference between these two bands. In other words, the wavelength of the emitted light is determined by a quantized electronic transition. This is not an emergent effect. It is the direct result of the probabilistic nature of electrons existing in discrete, non-continuous energy states. The predictability and reproducibility of these transitions allow engineers to design LEDs that emit with remarkable efficiency and specificity. The materials used in LEDs are carefully selected and structured on the atomic level to produce desired emission properties. Gallium arsenide, gallium nitride, and indium phosphide are some of the compound semiconductors used in modern LEDs. These materials are engineered through techniques such as molecular beam epitaxy and metal-organic chemical vapor deposition, which allow scientists to grow crystal layers atom by atom with precise control over thickness, composition, and electronic structure. In many high-efficiency LEDs, quantum wells, nanoscale layers only a few atoms thick, are used to further confine electrons and enhance their likelihood of radiative recombination. These quantum wells exploit another fundamental quantum principle. The confinement of particles increases their energy and modifies their behavior, allowing fine-tuned control over the properties of the emitted photons. This is also why LEDs are so much more energy efficient than incandescent bulbs. Traditional bulbs produce light by heating a filament until it glows, radiating energy as blackbody radiation across a wide spectrum, most of which is wasted as heat. In contrast, LEDs convert electrical energy directly into light with minimal thermal loss. The photons produced by an LED emerge with nearly the same energy as the electrons that generated them. This high efficiency is possible only because of quantum predictability. The electron transitions are not random. They follow strict rules governed by the band structure of the material and conservation laws. In this sense, an LED is an engineered manifestation of quantum laws. If LEDs represent the controlled emission of light from spontaneous quantum events, lasers represent the quantum phenomenon of stimulated emission amplified to extraordinary coherence. The word laser is an acronym for light amplification by stimulated emission of radiation. This is not merely a technological term, it directly describes the quantum process at the heart of laser operation. Stimulated emission occurs when an incoming photon of a specific energy interacts with an excited electron in an atom or molecule. If the energy of the photon matches the energy difference between two electronic states, the electron will drop to the lower state and release a second photon that is identical in every way to the incoming one. Same energy, same phase, same direction. Unlike the spontaneous emission in LEDs, this process is coherent. The emitted photons are synchronized with the stimulating photon. This is a purely quantum event with no classical analog. Lasers work by creating a population inversion, more electrons in excited states than in ground states, in a gain medium. This inversion is sustained by pumping the medium with external energy, such as electrical current or another light source. Once inversion is achieved, a photon passing through the medium can trigger a cascade of identical photons via stimulated emission. Mirrors at either end of the medium reflect the light back and forth, amplifying it further until it exits through a partially transparent mirror as a highly focused, coherent beam. The coherence and directionality of laser light emerge solely because of the quantized nature of light and matter. Classical physics cannot explain why all photons in a laser beam are identical. This phenomenon arises from the indistinguishability of quantum particles and the way they interact in phase-matched systems. Even the stability of a laser's output depends on maintaining coherence across many quantum transitions, all synchronized through the architecture of the laser cavity. The applications of lasers in daily life are too numerous to list in detail, but their ubiquity is a testament to how deeply quantum phenomena have been woven into modern existence. Lasers are used in fiber optic communication, barcode scanners, medical surgery, construction alignment tools, computer mice, and optical storage devices such as DVDs. In all these cases, the ability to produce precise, intense, and coherent light is indispensable. Yet none of this would be possible without understanding and exploiting the rules of quantum emission. It's worth noting that laser technology has evolved far beyond simple red beams. Today, lasers operate across the electromagnetic spectrum, from infrared to ultraviolet, and can be tuned with extreme precision. Quantum cascade lasers, for instance, use engineered nanostructures to produce mid-infrared light, useful in gas sensing and spectroscopy. These devices rely not on discrete atomic transitions, but on inter-subband transitions within quantum wells, engineered energy levels that emerge from nanoscale confinement. Again, this is quantum control at its most advanced, where even the energy levels themselves are fabricated to fit human design. There are also mode-locked lasers that generate pulses lasting only femtoseconds, quadrillionths of a second, allowing scientists to observe and manipulate ultra-fast chemical reactions. Such pulses are not just short, they are coherent across time and frequency, a property made possible only by managing quantum phase relationships. These pulses allow experiments where molecules are probed in mid-reaction, letting researchers glimpse the very formation and breaking of chemical bonds. Both LEDs and lasers exemplify how quantum mechanics has moved from theoretical obscurity to technological dominance. They are not based on metaphorical interpretations of wave-particle duality or philosophical debates about observation. They are engineered devices grounded in precise quantum models. Quantum electrodynamics, the most accurate physical theory ever tested, underpins our understanding of how electrons and photons interact. And it is through this understanding that light itself has been brought under human control. This chapter of modern physics is still being written. Quantum light sources are being developed for quantum computing and communication systems, where single photon sources, LED-like devices that emit one photon at a time, are necessary for secure data transmission and quantum logic operations. These devices require even finer control over quantum behavior, including entanglement and coherence at the single particle level. At the forefront of these developments, engineers are crafting light itself into a tool for processing information in fundamentally new ways. It's easy to forget, standing in the glow of a screen or scanning a code at checkout, that every point of light you see from an LED or laser beam is the final step in a quantum journey. Each photon began as a probability, a potential energy transition between states, and only in the act of recombination was it born into reality. The light that reaches your eyes, so stable and predictable, is a cascade of events that at its heart is uncertain, statistical, and purely quantum. And perhaps in those moments when you are surrounded by light, artificial yet perfectly tuned, you might consider what that light really is. Not merely illumination, but the echo of electrons falling through invisible stairways. A universe where every color, every spark, every coherent beam was once just a possibility among many. And yet, here it is, shining quietly before you, as if the cosmos itself chose to express its quantum rules in beams and pulses of certainty. Chapter 4. The magic of quantum tunneling in your hard drive. Deep within the solid structure of your computer or smartphone, buried beneath polished metal casings, below the warmth of the processor, beyond the reach of your senses, there are electrons performing a feat that defies the ordinary logic of the physical world. These electrons are not following the smooth curves of classical paths. They are doing something more elusive, more counterintuitive. They are passing through barriers they should not be able to cross. This phenomenon is known as quantum tunneling, and it is the quiet engine behind much of the world's modern data storage. In classical physics, a particle with insufficient energy cannot overcome a barrier. Like a ball rolling up a hill, if the initial kinetic energy is too low, the ball will slow, stop, and roll back down. There is no ambiguity, but quantum particles do not obey such certainties. Due to their wave-like nature, there is a probability, however small, that they can tunnel through a barrier and appear on the other side, even when their energy is not enough to surmount it. It is as though the ball does not climb the hill, but simply appears on the other side, having passed through a region it had no classical right to enter. This is not a metaphor. It is a measurable, testable, and predictable property of quantum systems. And it lies at the heart of many technologies we now depend on, including the most fundamental act a computer can perform: storing and retrieving information. To understand this more deeply, consider how data is stored in non-volatile memory, like the flash memory used in solid-state drives, SSDs, and USB sticks. Unlike older mechanical hard drives, SSDs store data without moving parts. They rely on an architecture built around transistors, specifically floating-gate transistors. These transistors have a layer designed to trap and hold electrical charge, which represents a binary 1 or 0 depending on whether the floating gate is charged. But how does that charge get into such a small, isolated region of material? The answer lies in quantum tunneling. During a write operation, a high voltage is applied to the transistor. This voltage is strong enough to enable electrons to tunnel through a thin, insulating layer of oxide and become trapped in the floating gate. Classically, this layer is a barrier. Electrons should not be able to pass through it. But at the nanometer scale, the probability of tunneling becomes significant. The thickness of the oxide is often only a few nanometers, just tens of atoms across. At this scale, the barrier is not impenetrable. It is semi-permeable to quantum particles. Once the electrons are inside the floating gate, they remain trapped even when power is removed. This is what allows flash memory to retain information without continuous energy input. To erase the data, another voltage pulse is used to pull the electrons back across the barrier, again via quantum tunneling. The act of writing and erasing data, then, is not a matter of pushing charges along channels, but of delicately managing the probabilities of electrons appearing on the other side of forbidden zones. The design of these memory cells involves extreme precision. Engineers must carefully control the thickness of the insulating layer, the materials used in the gate, and the voltages applied. If the oxide layer is too thick, tunneling is impossible. If it's too thin, stored electrons may leak out over time, corrupting the data. This leakage is also a tunneling effect, an undesired one, and it must be minimized. The reliability of modern memory storage thus depends on a careful balancing act, allowing electrons to tunnel when desired, but remain confined otherwise. It's a choreography of probability, crafted from the rules of quantum physics. Quantum tunneling also plays a role in magnetic storage devices, such as hard disk drives, HDDs, which, despite being increasingly replaced by SSDs, still serve as the backbone of data centers and archival systems. In magnetic tunnel junctions used in magnetoresistive random access memory, MRAM, and some read-head technologies, quantum tunneling is used to detect the magnetic orientation of nanoscale regions on a disk. A magnetic tunnel junction consists of two ferromagnetic layers separated by a very thin insulating layer. One of the magnetic layers has a fixed orientation. The other can be changed. The resistance of the junction depends on whether the magnetic orientations are aligned or opposed. When the orientations are parallel, electrons are more likely to tunnel through the barrier. When they are anti-parallel, tunneling is suppressed. The change in resistance is measurable and corresponds to a binary state. Again, this effect depends on the wave nature of electrons and their ability to penetrate forbidden regions, a behavior with no classical explanation. In scanning tunneling microscopes, STMs, this principle is used to image surfaces with atomic resolution. A sharp metallic tip is brought extremely close to the surface of a sample, so close that electrons can tunnel between the tip and the sample, even though no actual contact is made. By measuring the tunneling current as the tip scans across the surface, the microscope constructs an image of the electron density of the sample. This level of detail would be impossible without tunneling, as no classical tool could probe structures so small without physically touching or disturbing them. While STMs are research tools, the knowledge they provide feeds directly into materials engineering, helping scientists design better magnetic media and memory components. The precise arrangement of atoms, the structure of energy barriers, and the properties of thin film materials are all informed by data gathered through tunneling-based instruments. The very feasibility of miniaturizing electronics to their current scale hinges on tunneling. As devices shrink to dimensions measured in nanometers, the barriers between components become so thin that tunneling currents arise even when not desired. These currents can lead to power leakage, thermal waste, or even logic errors. But rather than treating tunneling solely as a problem, modern semiconductor design has embraced it. In tunneling field effect transistors, TFETs, engineers intentionally use tunneling to switch devices on and off, aiming for lower power consumption and faster response. In this way, tunneling is not a side effect. It becomes the switching mechanism itself. The transition from classical transistor operation to quantum-enabled switching is a profound shift. It reflects the ongoing convergence of quantum theory and everyday engineering. The more we miniaturize, the more the rules of quantum mechanics become not just relevant, but dominant. Engineers now routinely use quantum models in the design phase. They simulate the behavior of electrons as wave functions, solve Schrödinger equations numerically, and optimize materials to produce desired tunneling probabilities. In effect, every modern hard drive, memory stick, or solid-state array is a product of applied quantum theory. This influence extends even further. Quantum tunneling has inspired entirely new types of storage. Research into resistive RAM, ReRAM, and phase change memory, PCM, continues to explore how atomic scale changes in material structure, driven by electrical fields and thermal effects, can be used to create fast, durable, and low-power memory. Many of these behaviors involve tunneling phenomena and electron localization, where quantum mechanical interactions dominate the physical state of the device. What is remarkable is how seamlessly these quantum effects have been woven into consumer products. The average user has no sense that their photographs, messages, or documents are stored using processes that rely on quantum indeterminacy. Data is saved and retrieved millions of times each day by electrons slipping silently through barriers, probabilistically appearing in new places, governed not by force but by likelihood. There is no dramatic spark, no visible sign of their passage, only the quiet reliability of memory that holds until erased. Yet every stored file is a fingerprint of quantum behavior made stable through engineering. What once seemed like an abstract corner of physics has become the most practical of all tools, a means of remembering, of storing history, of organizing thought and communication. And perhaps in this understanding there is a humbling realization that your memories, digital ones at least, exist not in some fixed mechanical vault, but in a system that rests on uncertainty, on the likelihood of presence, on fields and probabilities. Each file you save is kept alive by a dance of electrons tunneling through walls, navigating invisible dimensions, persisting not through solidity, but through quantum choreography. You might never see them. You might never feel their journey. But inside every hard drive, every chip, every memory cell, the improbable happens billions of times per second. The boundaries of the physical world bend, not break, to allow the passage of the quantum traveler. And in that quiet passage, your digital life finds its place. Chapter 5. Quantum Effects in Medical Imaging and Diagnosis. When you walk into a hospital for a scan, whether it's for an MRI, a CT scan, or a PET scan, you are entering a realm where some of the most complex and abstract principles of physics quietly serve one of the most intimate human needs: to look within. We often think of medicine and physics as distant disciplines, separated by their objectives and language. But inside the hum of a diagnostic machine, quantum physics is at work, probing tissues, measuring fields, and rendering the invisible visible. Medical imaging, in its modern form, would not exist without the insights of quantum mechanics. At its core, imaging is the task of gathering data from systems that cannot be directly accessed. The body is opaque to visible light, and the scale of molecular and atomic structure is far below the resolution of classical lenses. But quantum phenomena offer tools that can bypass these limitations, not by pushing harder, but by thinking differently about how particles and energy interact. One of the most striking examples of this is magnetic resonance imaging, or MRI. This technology is based on the spin of atomic nuclei, a purely quantum mechanical property that has no classical counterpart. In classical terms, spin might be imagined as a kind of rotation, but this metaphor quickly breaks down. Spin is intrinsic. It is not the result of motion in space, but rather a built-in quantum property, much like charge or mass. In biological tissue, the most common nuclei with non-zero spin are hydrogen atoms, which are abundant because of water and fat content. When a patient enters the bore of an MRI machine, they are surrounded by a powerful, uniform magnetic field. This field causes the spins of the hydrogen nuclei to align with or against the field direction, creating a small net magnetization in the body. However, these spins are not locked in place. They precess or wobble around the magnetic field axis at a specific frequency, the Larmor frequency, which depends on the strength of the magnetic field and the type of nucleus. By sending in radio frequency pulses tuned precisely to this frequency, the MRI machine can tip the net magnetization away from alignment. When the pulse stops, the spins gradually return to their equilibrium state, emitting faint radio signals as they do so. These signals are picked up by coils and transformed into images. The way these spins return to equilibrium varies depending on the tissue environment, such as differences in water content, molecular composition, or blood flow, and these variations provide contrast in the resulting images. The level of control required here is astonishing. Radio pulses are engineered to manipulate the collective behavior of billions of individual quantum systems, each hydrogen nucleus behaving like a tiny magnet. The machine's software models their relaxation times, T1 and T2, both quantum mechanical parameters that describe how quickly the spins return to equilibrium in different ways. These decay times depend on interactions between spins, molecular motion, and the quantum environment of the tissue. What emerges on the screen is not a direct visual of organs or cells, but a reconstruction of quantum relaxation behaviors. In more advanced forms of MRI, such as functional MRI, fMRI, the imaging is not just structural but dynamic. By tracking changes in blood oxygenation, another effect that subtly alters the local magnetic environment, fMRI allows scientists to monitor brain activity in real time. It is a non-invasive way of eavesdropping on the quantum spin dynamics of molecules within living tissue. Another powerful tool that relies on quantum effects is positron emission tomography, or PET. This technique involves the detection of gamma rays produced by a process that begins with quantum decay. Patients are injected with a compound labeled with a positron-emitting radionuclide, commonly fluorine-18. As this isotope decays, it emits a positron, the antimatter counterpart of the electron. When this positron encounters an electron in the body, they annihilate, converting their mass into energy in the form of 2 gamma photons emitted in opposite directions. These photons are detected by an array of sensors surrounding the body. Because they travel in precisely opposite directions, the system can infer the origin of the annihilation event. With enough data, a 3D image of metabolic activity can be reconstructed. This allows doctors to detect cancer, monitor organ function, and investigate neurological disorders, not by observing tissues directly, but by measuring the quantum decay signatures of subatomic particles. PET imaging is a remarkable example of using quantum mechanics not only as a tool of theory, but as a literal window into the body. The entire process, from the radioactive decay governed by the weak nuclear force, to the annihilation events, to the detection of photons, operates according to the rules of quantum field theory. There is no classical analog for matter-antimatter annihilation. It is a uniquely quantum phenomenon, harnessed with precision and safety to improve human health. Even in X-ray imaging and computed tomography, CT, quantum ideas are indispensable. X-rays themselves are high-energy photons, and their interaction with matter, especially the attenuation they experience when passing through different tissues, is governed by quantum probabilities. The photoelectric effect, in which photons transfer their energy to inner shell electrons and eject them from atoms, was one of the first phenomena to be explained by quantum theory. Einstein's work on this in 1905 laid the foundation for understanding how photons interact with matter in discrete energy packets, rather than continuous waves. In CT scans, X-rays are passed through the body from multiple angles, and the varying degrees of absorption are used to build a volumetric map of the body's interior. This technique is possible because we can model how different tissues interact with photons of specific energies. Bone absorbs more X-rays due to its high density and atomic number, while soft tissues absorb less. These absorption rates are quantifiable thanks to quantum electrodynamics, which predicts how photons interact with atomic electrons. Digital X-ray detectors, used in both CT and standard radiography, are often based on photodiodes, devices that rely on the photoelectric effect. When X-ray photons strike the detector material, they generate electron-hole pairs, producing a current that is measured and converted into an image. The entire detection mechanism is thus built on quantum transitions within solids. In nuclear medicine more broadly, other techniques like single-photon emission computed tomography, SPEC, rely on the behavior of gamma photons emitted from radioactive tracers. These methods combine chemistry, quantum physics, and biology to generate diagnostic images that are highly specific and sensitive. The decay of these tracers is governed by quantum rules, particularly the probabilistic nature of nuclear transitions. The half-life of a radionuclide is not a deterministic value, but a statistical one, emerging from the fundamental uncertainty embedded in quantum mechanics. At the edge of current research, quantum sensors are being developed that could revolutionize medical diagnostics. These devices aim to measure extremely small magnetic fields, such as those produced by neural activity or the beating of the human heart, with unprecedented sensitivity. Some of these sensors use nitrogen vacancy centers in diamond, which are atomic-scale defects that can detect magnetic resonance signals at the level of single molecules. These systems function only because the quantum spin states of the defect can be initialized, manipulated, and read out at room temperature, making them suitable for biological environments. Another frontier is quantum-enhanced MRI, where entangled states and squeezed spin ensembles are being explored to surpass classical noise limits and enhance image resolution. Though these methods are still largely in the realm of experimentation, they represent a merging of medical needs with the most advanced tools of quantum science. Quantum computing may one day further expand diagnostic capability by simulating molecular interactions in ways classical computers cannot. Such simulations could help predict protein folding, enzyme function, or drug binding, key factors in understanding disease mechanisms. While not strictly imaging in the traditional sense, these simulations could offer a new layer of insight, seeing disease at the quantum level before it manifests at the macroscopic scale. Despite the profound complexity behind these methods, the experience for the patient is often quiet and simple. Lie still, wait, breathe. But beneath that stillness, machines hum with energy calibrated to manipulate and detect quantum states. The hydrogen nuclei in your body respond to magnetic fields with quantum precision. Radioactive atoms decay with timing born of probabilistic laws. Photons interact with your tissues in ways predicted by equations written over a century ago. And detectors translate these interactions into pictures that guide surgery, diagnose disease, and monitor recovery. The fusion of quantum mechanics with medicine is one of the great triumphs of applied science. It bridges a world of uncertainty and abstraction with the urgent needs of human life. We use the indeterminacy of particles to make the diagnosis more certain. We use the invisibility of fields to help us see. We use the delicate states of matter to strengthen our understanding of flesh and bone. And perhaps after the scan is complete and the image is rendered, a deeper truth remains. That inside your body, every cell, every molecule, every atom is a system governed by the same strange rules that shape the stars and the vacuum of space. You are not separate from the quantum world. You are a structure it has built, patterned, layered, living. In every pulse of a magnet, every flicker of a photon, it reveals itself to you. Not from beyond, but from within. Chapter 6: Atomic Clocks and the Quantum Nature of Timekeeping. To most of us, time is a given. It appears to flow effortlessly forward, measured by the tick of a wristwatch or the rhythm of a pendulum. It governs our days, our appointments, our lives. But beneath this familiarity lies a more fundamental question. What exactly is time? And how can we measure something that is not a substance or a field, but a relationship between events? In our pursuit of this measurement, we have turned not to swinging arms or mechanical gears, but to the quantum realm, where time, paradoxically, is measured by transitions that exist outside of time itself. Atomic clocks are the most accurate timekeeping devices humanity has ever constructed. They do not rely on moving parts or celestial motions, but instead harness the internal properties of atoms, properties that arise from quantum mechanics. At the core of an atomic clock is a system so small, so delicate, that its behavior can only be described by quantum theory. And yet, from this quantum system emerges the most stable and precise tick-tock rhythm ever achieved. The fundamental idea behind atomic clocks is to use the oscillations of atoms as a reference for time. all atoms have electrons arranged in quantized energy levels. These levels are fixed and immutable for a given element. When an electron jumps between two energy levels, it absorbs or emits electromagnetic radiation at a frequency that is unique and consistent. This frequency, corresponding to the energy difference between the two levels, becomes the basis of the clock. The most commonly used atom in high-precision timekeeping is cesium-133. The cesium atomic clock defines the official second in the International System of Units, I. According to this standard, 1 second is defined as the duration of 9,192,631,770 oscillations of radiation, corresponding to the transition between two hyperfine levels of the ground state of the cesium-133 atom. This number is not arbitrary, it is the natural resonance of the atom itself, and it arises from the quantum mechanical interaction between the magnetic moments of the nucleus and the surrounding electrons. In practical terms, cesium atoms are placed in a vacuum chamber and exposed to a stream of microwave radiation. The frequency of the radiation is adjusted until it matches the transition frequency of the cesium atoms. When the resonance condition is met, the atoms absorb the radiation and transition to a higher energy state. Detectors monitor this process, and feedback loops continuously adjust the microwave source to stay locked to the precise resonance. The result is a signal that can be counted, each cycle of the microwave radiation corresponding to a minuscule, perfectly predictable increment of time. This process depends entirely on quantum stability. The energy difference between atomic levels is set by the fundamental constants of nature: the Planck constant, the mass of the electron, the fine structure constant, and the specific configuration of the atom. These constants do not vary. The cesium atom resonates today exactly as it did a century ago, and exactly as it will in 1 billion years, barring cosmological shifts. This makes it a nearly perfect timekeeper, not because we trust the atom, but because nature does. Over time, scientists have developed even more precise atomic clocks by moving to atoms like rubidium, hydrogen, and more recently, strontium and ytterbium. These atoms can be trapped and cooled using lasers in what are known as optical lattice clocks. Instead of using microwave frequencies, these clocks use visible or near-visible light to drive transitions, frequencies that are about 100,000 times higher than those in cesium clocks. Because these transitions occur more rapidly, they can be counted more precisely, allowing for an even finer resolution of time. To put this into perspective, modern optical lattice clocks are so accurate that they would not lose or gain a single second over the lifetime of the universe. They can detect gravitational time dilation, a prediction of Einstein's general relativity, by being raised just a few centimeters. In such clocks, even moving the device from the bottom to the top of a stairwell results in a measurable difference in the passage of time, because time itself flows differently depending on the strength of the gravitational field. This extraordinary sensitivity has profound implications for science and technology. Global positioning systems, GPS, for example, rely on atomic clocks aboard satellites to provide precise time signals. The system works by measuring the time it takes for a signal to travel from a satellite to a receiver on Earth. Given the speed of light, even a nanosecond error in timekeeping could result in a position error of several meters. To maintain accuracy, GPS satellites must account not only for the time measured by their onboard atomic clocks, but also for the effects of both special and general relativity. The satellite's motion causes time to slow slightly, a special relativistic effect, while its altitude causes time to speed up, a general relativistic effect. These corrections are calculated and applied routinely, without which GPS would drift into uselessness within hours. Beyond navigation, atomic clocks are used in telecommunications to synchronize data transmission across vast networks. Financial markets rely on synchronized timestamps to execute trades across continents. Scientific experiments involving radio telescopes or particle accelerators depend on coordinated timing to within billionths of a second. In all of these cases, quantum timekeeping is not a convenience, it is a necessity. Interestingly, atomic clocks have also opened the door to new kinds of research. By monitoring the stability of atomic frequencies over time, scientists can test fundamental laws of physics. For instance, if any of the so-called constants of nature were to vary, even minutely, the frequencies emitted by atomic transitions would shift. By comparing different types of atomic clocks over months or years, researchers can test whether the fine structure constant or other parameters are truly constant. So far, no variation has been observed, but the very act of testing connects timekeeping to cosmology, uniting the most human of measurements with the deepest structure of the universe. At the heart of this precision lies one of the most remarkable features of quantum mechanics, that it allows systems to be isolated, manipulated, and measured with extraordinary control. Atoms in a trap can be cooled to near absolute zero, minimizing thermal motion and reducing uncertainty. Lasers can be tuned to interact with specific transitions. Magnetic fields can be applied to reduce external influences. In each case, the goal is the same: to create a quantum system so pure that its natural rhythm becomes a beacon of time itself. And yet, despite this precision, time remains elusive. In quantum mechanics, time is not an operator like position or momentum. It is a parameter, not something that can be measured directly in the same sense as other quantities. This asymmetry has puzzled physicists for decades. In relativity, time and space are unified into space-time. In quantum theory, time simply flows, a background against which probabilities evolve. Some physicists argue that time itself might emerge from entanglement or information flow, suggesting that our most basic intuitions about it are incomplete. Still, for all its philosophical ambiguity, time as measured by atomic clocks is concrete, practical, and astonishingly precise. It is this paradox of an abstract quantity pinned down by quantum certainty that makes atomic clocks so compelling. They are both tools and metaphors. Tools, because they regulate communication, science, defense, and economics. Metaphors, because they show how something as fluid as time can emerge from the stability of invisible, vibrating atoms. Every beat of an atomic clock is a whisper from the quantum realm. It tells us that the universe, in its deepest layers, is not chaotic but patterned. That change can be measured, not because we impose structure on nature, but because nature provides its own rhythm. That rhythm is not the swing of a pendulum or the turning of a gear, but the oscillation of electrons between well-defined quantum states, states governed by rules that have held across eons. And perhaps, as you glance at the time displayed on your device, down to the millisecond, you might consider what lies beneath it. That every digital tick is synchronized with cesium atoms resonating in distant laboratories. That your schedule, your heartbeat, your very perception of order unfolds in step with particles that hum in harmony with the universe itself. You are not just tracking time, you are listening to the universe count. Chapter 7: Secure Communication, Quantum Cryptography and You. In an age where communication is constant, where billions of messages pulse through fiber optic cables and wireless networks every moment, the question of privacy has become both more urgent and more fragile. From bank transactions and corporate data to national secrets and personal conversations, information flows at the speed of light. And in that relentless flow, security is everything. But no encryption system, however intricate, is immune to the looming evolution of computation, particularly the rise of quantum computers. In response, scientists have turned to the very same quantum mechanics that could one day threaten classical cryptography, using its paradoxes and constraints not as vulnerabilities, but as shields. This is the foundation of quantum cryptography, a method of communication that is not just secure in practice, but in principle. At the heart of secure communication lies the concept of a cryptographic key, a string of bits used to encrypt and decrypt messages. Traditional encryption methods, such as RSA or elliptic curve cryptography, rely on the mathematical difficulty of certain problems, like factoring large numbers or solving discrete logarithms. These problems are computationally hard for classical computers, and that hardness is what ensures the security of the data. However, quantum algorithms, most notably Shor's algorithm, can solve these problems exponentially faster, rendering traditional encryption potentially obsolete once scalable quantum computers are realized. Quantum cryptography offers a solution not by making problems harder, but by changing the rules entirely. It exploits fundamental properties of quantum systems, such as superposition, entanglement, and the no-cloning theorem, to create encryption methods that cannot be broken, even in theory, without detection. The most prominent application of this approach is quantum key distribution, or QKD. The goal of QKD is to allow two parties, traditionally named Alice and Bob, to establish a shared cryptographic key over an insecure channel in such a way that any attempt to eavesdrop on the exchange can be detected. The most well-known protocol for QKD is the BB84 protocol, proposed by Charles Bennett and Gilles Brassard in 1984. It uses individual photons, the quantum particles of light, as carriers of information. Each photon is prepared in one of several possible quantum states, such as specific polarizations. Due to the principles of quantum mechanics, measuring a photon in the wrong basis disturbs its state and introduces detectable errors into the system. When Alice sends a sequence of randomly chosen polarized photons to Bob, he attempts to measure each one using a randomly chosen basis. After the transmission, they publicly compare which bases were used, discarding any results where they mismatched. The remaining shared results form the raw key. If an eavesdropper, commonly named Eve, tries to intercept the transmission and measure the photons, she inevitably introduces detectable errors because she cannot know which basis to use for each photon. This is a direct consequence of the uncertainty principle and the impossibility of perfectly cloning an unknown quantum state. Any intrusion into the channel becomes evident through statistical analysis. If the error rate exceeds a certain threshold, Alice and Bob know that the key has been compromised and discard it. If the error rate remains low, they can apply privacy amplification and error correction techniques to produce a final key that is virtually guaranteed to be secure. This level of security is not based on complexity. It is not built on how long it would take a computer to break the system by brute force. It is based on the laws of nature themselves. The security of QKD rests on the fact that quantum measurement is inherently invasive. There is no way to passively observe a quantum system without changing it. This is not a technological limitation, but a fundamental property of quantum information. Beyond the BB84 protocol, more advanced versions of QKD have been developed, including protocols that use entangled particles. In these systems, pairs of photons are generated in a quantum entangled state and sent to Alice and Bob. When they measure their photons, the results are correlated in ways that violate classical expectations, confirming that entanglement is present. This kind of QKD can be more robust and allows for certain forms of device-independent security, where the internal workings of the devices do not need to be trusted for the protocol to remain secure. These entanglement-based systems make use of Bell's inequalities, mathematical expressions that distinguish between quantum and classical correlations. Violations of these inequalities demonstrate that the communication channel cannot be described by any local realistic theory. In simpler terms, they prove that the data is governed by quantum rules and that any eavesdropping attempt would disrupt the entanglement and alter the measurement outcomes. Quantum cryptography is already being deployed in specialized networks around the world. Fiber-based QKD has been demonstrated over hundreds of kilometers, and satellite-based QKD has enabled secure key distribution between continents. In 2017, China's Michia satellite successfully conducted quantum key exchange between ground stations separated by more than 1,000 kilometers, marking a significant milestone in global quantum communication. However, these systems are not without challenges. Quantum signals are extremely delicate. Photon loss in optical fibers, decoherence due to environmental interactions, and detector inefficiencies can all degrade performance. Moreover, while QKD secures the key exchange, it does not encrypt the data itself. It must be integrated into larger cryptographic frameworks to be truly effective. Nevertheless, the promise of quantum cryptography lies in its conceptual invulnerability. Unlike classical cryptographic systems, which may be broken with future mathematical breakthroughs or more powerful machines, quantum-secured communication offers a guarantee rooted in physics. It is not just that breaking the system is hard, it is that it would violate the very structure of quantum mechanics. Quantum cryptography also inspires deeper questions about the nature of information. In quantum theory, information is physical. It is not abstract. It cannot be copied arbitrarily. This contrasts sharply with our classical intuition, where information is something that can be duplicated, transmitted, and shared freely. In the quantum world, information has boundaries. It is embedded in the state of systems and constrained by what is knowable. The no-cloning theorem ensures that quantum information cannot be perfectly replicated. The act of measurement creates outcomes, but erases alternatives. These constraints are not limitations. They are the features that make unbreakable cryptography possible. In this sense, quantum cryptography is more than just a technological innovation. It is a redefinition of what secrecy means. It shifts our view of security from one of control to one of coherence. To communicate securely in the quantum age is not to build a stronger wall. It is to ensure that any attempt to climb the wall leaves footprints. The implications of secure quantum communication stretch far beyond personal privacy. As nations, corporations, and institutions increasingly rely on digital systems, the stakes of data breaches grow ever higher. The development of quantum-resistant encryption and quantum-secured channels is already a matter of strategic interest. In parallel, work on post-quantum cryptography, classical algorithms believed to be secure even against quantum computers, is ongoing. Yet even here, quantum cryptography offers a distinct and complementary approach, one that sidesteps the arms race of algorithmic complexity and instead turns to nature's own protective mechanisms. Looking ahead, quantum networks may form the backbone of a future quantum internet, an infrastructure that not only transmits data, but also distributes entangled states, synchronizes atomic clocks, and enables new forms of distributed quantum computation. Such a network would be more than a communication system. It would be a shared quantum resource, spanning continents and connecting devices through entanglement itself. And all of this begins with the most basic desire: to speak, to share, to trust. That even in a world where data flows in unseen rivers, there can still be places where secrecy is sacred, not by decree, but by design. Perhaps that is the most poetic outcome of all. That in the strange, delicate behavior of particles, uncertain, unknowable, indivisible, we have found the most reliable foundation for something as human as privacy. That every secure message, every protected thought, may one day travel through a channel not defended by barriers, but by principles. That in the quantum shadows, where information flickers and collapses, your secrets can rest more safely than ever before. Chapter 8. Quantum sensors that can hear the unhearable. In a world where technology often focuses on speed, power, or scale, there exists a quieter frontier, one devoted not to how fast we can compute or how far we can transmit, but to how delicately we can listen. This is the domain of quantum sensing, where the goal is not brute force detection, but a sensitivity so refined that it borders on the miraculous. These are instruments built not to amplify noise, but to reveal signals so faint, so subtle, that they would be otherwise lost to the chaos of the environment. And at their heart lie the very principles of quantum mechanics: superposition, entanglement, and coherence, harnessed not to model reality, but to measure it. Quantum sensors differ from their classical counterparts in both principle and performance. They do not merely push the limits of engineering, they redefine what is measurable. By exploiting the peculiar properties of quantum systems, these sensors can detect changes in position, field, or energy at scales that classical physics cannot reach. They are capable of measuring gravitational shifts from a passing truck, detecting a neuron firing in the brain without invasive probes, or sensing the trace presence of single molecules in the air. To understand how this is possible, one must begin with the idea of quantum coherence. In a quantum system, coherence refers to the ability of a particle or ensemble of particles to exist in a well-defined superposition of states. This superposition is fragile. It can be disturbed by thermal noise, electromagnetic fields, or even the mere presence of an observer. But when preserved, coherence allows quantum systems to be extraordinarily sensitive to external perturbations. A slight change in magnetic field, a minute shift in gravitational potential, or a subtle chemical interaction can all cause a measurable change in the state of the system. The key is not to overpower the noise, but to listen in its absence. One of the most promising platforms for quantum sensing is the nitrogen vacancy NV center in diamond. An NV center is a defect in the diamond lattice, where a nitrogen atom replaces a carbon atom adjacent to a vacancy. This imperfection creates a localized electronic state with unique quantum properties. At room temperature, NV centers can be optically excited and read out using lasers and microwaves. They can be used to detect magnetic fields, temperature variations, and electric fields with remarkable spatial resolution. The reason NV centers are so powerful lies in their spin states. These states can be initialized with light, manipulated with magnetic resonance techniques, and read out via photoluminescence. When an external magnetic field is applied, it shifts the energy levels of the spin states, a phenomenon known as the Zeeman effect. This shift changes the fluorescence signal, allowing for a precise measurement of the field strength. Because of their atomic scale, NV centers can be embedded in nanodiamonds, introduced into biological systems, and used to map neural activity, detect pathogens, or even monitor intracellular temperatures. In another approach, atomic interferometry uses the wave nature of atoms to measure acceleration, rotation, and gravitational potential. By cooling atoms to near absolute zero and placing them in a coherent superposition of momentum states, researchers can let these atoms travel along different paths and then recombine them. The interference pattern that results contains information about the external forces experienced during their separation. Atomic interferometers have been used to test fundamental aspects of general relativity, measure local gravitational gradients, and develop ultra-sensitive accelerometers and gyroscopes. Unlike traditional mechanical systems, these atom-based devices are not subject to friction or wear. Their resolution is limited only by quantum uncertainty and technical noise, both of which can be minimized through isolation and error correction. In navigation, where GPS signals may be blocked or unavailable, such as in submarines or spacecraft, quantum accelerometers could allow autonomous systems to maintain accurate positioning over long durations, purely by measuring internal motion. Another frontier of quantum sensing is superconducting quantum interference devices, or SQUIDs. These instruments use superconducting loops interrupted by Josephson junctions, tiny regions where superconductivity is broken. When a magnetic field is applied, it induces a phase shift in the quantum wave function of the supercurrent, which can be detected with extraordinary sensitivity. Squids are among the most sensitive magnetometers ever built. They can detect changes in magnetic flux on the order of a few femtoteslas, several orders of magnitude smaller than the field produced by the human heart. Squids are already used in magnetoencephalography, EEG, a technique for mapping brain activity by measuring the magnetic fields generated by neural currents. Unlike EEG, which detects electrical potentials on the scalp, MEG provides a direct measurement of brain function at the source. The resulting data can offer insights into cognition, epilepsy, and neurological disorders, all while relying on a non-invasive quantum device. Even more exotic SING platforms are being explored using Bose-Einstein condensates, BECs, ultra-cold atomic gases that behave as a single quantum entity. In this state, atoms lose their individuality and share a common wave function. BECs are exquisitely sensitive to external forces because any perturbation affects the entire condensate collectively. They are being investigated for use in gravitational wave detection, dark matter searches, and fundamental physics experiments, where traditional detectors may lack the required sensitivity. Quantum sensing is also playing a growing role in chemistry and materials science. By using quantum probes to detect energy levels, spin states, or molecular interactions, researchers can study complex materials at the atomic scale. Techniques like electron spin resonance and nuclear magnetic resonance, which have long relied on quantum principles, are being enhanced with quantum algorithms and entanglement to increase resolution and reduce sample size. In medicine, these advances could lead to new diagnostics, early disease detection, and personalized treatment based on real-time molecular feedback. What unites all of these technologies is a shift in perspective. Rather than observing large systems from the outside, quantum sensors immerse themselves in the world they measure. They do not extract information by force, but by resonance. They tune themselves to the whisper of the environment and respond with exquisite fidelity. This is not merely a technical achievement, it is a philosophical one. It reflects a new relationship between measurement and reality, where the boundary between observer and observed becomes increasingly blurred. Moreover, quantum sensors are poised to reshape not only how we perceive the world, but how we interact with it. In earth science, portable gravimeters based on quantum interferometry can detect underground structures, water tables, or even volcanic activity. In security, quantum radar systems are being developed to detect stealth aircraft or concealed objects by using entangled photons that are immune to jamming. In environmental science, ultra-sensitive spectrometers can identify trace pollutants or greenhouse gases with unprecedented precision. Each of these breakthroughs carries with it the same foundational truth, that quantum mechanics is not only a theory of the invisible, but a tool for revealing what lies beneath. It transforms subtlety into data, transforms silence into signal. And yet the impact of quantum sensing is not limited to the laboratory or the instrument panel. It changes the way we think about perception itself. That the most detailed maps of the brain, the most accurate measurements of gravity, the faintest echoes of motion and magnetism, all come not from amplification, but from attention. From tuning into the wave-like properties of particles, from respecting the fragility of coherence, from listening where classical systems would be deaf. Perhaps the most beautiful lesson of quantum sensing is not what it reveals, but how it reveals it. That in a universe often perceived as indifferent and cold, there exists a layer of sensitivity, a realm where the smallest interactions can be measured with clarity, where the quietest fluctuations can tell a story. That you are surrounded not by silence, but by an orchestra too faint for ordinary ears. And maybe, just maybe, by learning to build instruments that can hear the unhearable, we also teach ourselves to pay attention more deeply. not only to the particles that pass through us unnoticed, but to the fleeting, delicate signals of the world and of ourselves. Chapter 9. Quantum Computers, the Next Leap. For decades, the progress of computation followed a familiar pattern. Transistors became smaller, processors faster, and memory more efficient. Moore's law, the observation that the number of transistors on a chip doubles approximately every 2 years, became a self-fulfilling prophecy. But as classical computing pushes against the limits of physical miniaturization and energy efficiency, a new approach is emerging from the quantum realm. It does not merely aim to make traditional computation faster. It redefines what it means to compute. Quantum computing is not a refinement of classical technology. It is a departure. It harnesses the principles of quantum mechanics, superposition, entanglement, and interference to process information in ways that have no classical equivalent. Where a classical bit can be either 0 or 1, a quantum bit or qubit can exist in a superposition of both states simultaneously. This allows a quantum computer to explore a vast space of possible solutions in parallel, dramatically increasing its computational power for certain classes of problems. But this power does not come easily. Qubits are fragile, easily disturbed by their environment. Maintaining coherence, that is, the stability of their quantum states, requires isolating them from sources of noise such as heat, electromagnetic radiation, or even mechanical vibration. Quantum systems must be cooled to near absolute zero, often using dilution refrigerators, and carefully shielded from the outside world. The control and measurement of qubits involve precise pulses of microwave or laser light, engineered with nanosecond accuracy. The physical realization of a qubit can take many forms. Superconducting circuits, trapped ions, neutral atoms, topological states, and photonic systems all offer viable paths to building quantum computers. Each platform has its strengths and weaknesses. Superconducting qubits, for example, are relatively fast and can be fabricated using existing semiconductor technologies, but they suffer from limited coherence times. Trapped ions exhibit excellent coherence but operate more slowly. Photonic qubits can move freely through optical fibers, making them well-suited for communication, but challenging to entangle in large numbers. Regardless of architecture, all quantum computers share a common foundation: the manipulation of quantum states through unitary operations, reversible transformations that preserve the total probability. These operations, implemented as quantum gates, form the basis of quantum algorithms. Unlike classical logic gates, which act on bits independently, quantum gates can entangle qubits, creating correlations that transcend classical logic. When qubits are entangled, the state of one cannot be fully described without reference to the other, even across great distances. This entanglement enables quantum algorithms to encode and process information in fundamentally new ways. Perhaps the most famous example is Shor's algorithm, which can factor large integers exponentially faster than the best-known classical methods. This has profound implications for cryptography, as many classical encryption schemes rely on the difficulty of factoring as a security foundation. Another example is Grover's algorithm, which provides a quadratic speedup for searching unstructured databases. While this might seem modest, it has wide-ranging applications in optimization, machine learning, and chemistry. Yet, the true power of quantum computing may lie not in replacing classical computers, but in complementing them. Classical computers excel at handling well-structured, deterministic tasks. Quantum computers, by contrast, are poised to revolutionize areas where the complexity of the system overwhelms classical methods, such as simulating quantum chemistry, solving optimization problems with vast numbers of variables, or modeling the behavior of materials at the atomic level. One of the most promising applications is in the simulation of molecular systems. The behavior of electrons in a molecule is governed by quantum mechanics, and predicting their interactions is computationally intensive. Classical methods must approximate wave functions using limited basis sets and iterative calculations. But a quantum computer, being a quantum system itself, can represent and manipulate these wave functions directly. This could lead to breakthroughs in drug discovery, material science, and energy storage, enabling researchers to identify catalysts, optimize reactions, and design new compounds with unprecedented precision. Another key application area is optimization, finding the best solution among many, often in scenarios with conflicting constraints. This arises in logistics, finance, network design, and machine learning. Quantum algorithms can explore solution spaces in parallel, exploiting interference patterns to amplify correct paths and suppress incorrect ones. While current quantum devices are not yet capable of solving these problems at scale, prototypes have demonstrated quantum-inspired techniques that already outperform certain classical heuristics. Despite the promise, quantum computing remains in its early stages. Most existing quantum processors are in the noisy intermediate-scale quantum (NISQ) era, meaning they contain between 50 and a few hundred qubits, with limited error correction and short coherence times. These systems are not yet capable of performing fault-tolerant computation, where logical qubits are encoded across multiple physical qubits to detect and correct errors. Achieving this requires quantum error correction codes, such as surface codes or concatenated codes, that can protect fragile quantum information against decoherence, gate errors, and measurement noise. Implementing error correction is a monumental challenge. It demands thousands of physical qubits for each reliable logical qubit and requires complex architectures to maintain entanglement and redundancy. Yet progress is steady. Researchers are already demonstrating small-scale logical qubits, and error rates are improving with each hardware generation. The race is now one of scale and fidelity, to build quantum computers with enough reliable qubits to run practical algorithms that outperform classical systems, an event known as quantum advantage or quantum supremacy. In 2019, Google claimed to have achieved this milestone by demonstrating a quantum processor that completed a specific task faster than any known classical computer. While the task itself had limited practical value, it served as a proof of principle. Other companies and institutions, including IBM, IonQ, Rigetti, and academic consortia, are building quantum platforms of increasing size and sophistication. Governments around the world have launched national initiatives to support quantum research, recognizing its potential to shape the technological landscape of the coming decades. The convergence of quantum computing with other disciplines, artificial intelligence, cryptography, and network science, suggests that its eventual impact may be more transformative than we can currently predict. Quantum machine learning, for example, seeks to combine the generalization power of neural networks with the high-dimensional structure of quantum systems. Quantum annealing offers another model of computation, where solutions emerge from the energy landscape of a physical system slowly evolving toward its ground state. Each of these approaches explores a different facet of the quantum computational universe. And yet, for all its mathematical elegance and engineering complexity, quantum computing is ultimately about possibility. It is the possibility of seeing patterns that were previously invisible, of exploring spaces that were computationally unreachable, of answering questions that were once left intractable. It is a reminder that nature's rules are not only strange, but useful, and that when we align our tools with those rules, we can achieve extraordinary things. Quantum computing also forces us to re-examine our assumptions about information. In classical systems, information is binary, discrete, and local. In quantum systems, it is continuous, probabilistic, and relational. A qubit does not carry a fixed value, but a superposition, a spectrum of possibilities. It becomes something definite only when observed, collapsing into a particular state. Computation, in this context, is not a mechanical process, but an evolution of possibility through the architecture of a designed quantum system. There is something profoundly humbling in this, that the act of calculating at its most fundamental level can no longer be separated from the rules of the universe that gave rise to it. That the abstraction of numbers and logic now relies on the coherence of atoms, the entanglement of particles, and the interplay of fields and symmetries. That when we compute in the quantum domain, we are not merely solving problems, we are conducting a dialogue with the fabric of reality itself. Perhaps, in the not-too-distant future, quantum computers will no longer be confined to laboratories or research centers. They may become tools as ubiquitous as today's microprocessors, embedded in scientific instruments, guiding autonomous systems, optimizing planetary-scale logistics, or unlocking the mysteries of complex biological systems. And when that happens, it will not be because we conquered nature, but because we learned to listen to it more carefully. And perhaps, as quantum circuits hum in supercooled silence, manipulating information not as static symbols but as entangled waves, we may come to understand that the limits we thought were final were only thresholds. That the next leap in computation is not just a leap in power, but a leap in thought. That in decoding the logic of the universe, we are also learning to reprogram the boundaries of our imagination. Chapter 10. Living with Quantum, a Quiet Reflection. As you move through your day, checking a message, turning on a light, navigating through a city, glancing at a clock, you are engaging with quantum mechanics in ways that are invisible, yet constant. The digital world, with all its convenience and capability, is increasingly built on principles that arise not from classical logic, but from the counterintuitive laws that govern atoms, photons, and electrons. It might seem that quantum physics belongs to the domain of theoretical physicists and particle colliders, but the truth is that the quantum world does not wait for you to observe it. You live in it, whether you notice it or not. Quantum mechanics was not designed to explain smartphones or encryption, yet it underpins them both. Its original intent was simply to make sense of phenomena that defied classical explanation. Why blackbody radiation didn't match predictions, why electrons and atoms didn't spiral into the nucleus, why light sometimes behaved like a wave and other times like a particle. In attempting to reconcile these contradictions, a new framework emerged. This framework, while initially abstract and disorienting, has turned out to be the most accurate and experimentally verified description of the physical world ever produced. The fact that quantum mechanics has enabled so many practical technologies is not incidental. The predictive power of its mathematics allows for the manipulation of nature at the smallest scales. Engineers can design semiconductors that precisely control electron flow. Chemists can model molecular orbitals to develop new drugs. Doctors can image the inside of the brain using nuclear spin states. Computer scientists are developing algorithms to exploit quantum entanglement for tasks classical computers cannot feasibly perform. The boundary between science fiction and functional technology is increasingly defined by the ability to work with, rather than against, quantum behavior. But this integration has not made quantum mechanics any easier to interpret. It remains a theory that resists intuitive understanding. The Copenhagen interpretation, long dominant, suggests that a quantum system exists in a superposition of states until measured. Other interpretations, many worlds, objective collapse, relational quantum mechanics, attempt to explain the same results in different conceptual languages. What they all agree on is that the behavior of the smallest constituents of reality does not mirror the predictability of everyday objects. Outcomes are probabilistic. Observation plays a central role. Causality becomes fuzzy. And yet, despite these philosophical puzzles, quantum mechanics remains unchallenged in its predictive accuracy. This odd duality, being both mystifying and operationally precise, defines how we live with quantum physics. The engineer does not need to interpret the wave function's metaphysical implications in order to design a working transistor. The radiologist does not need to resolve the measurement problem in order to read an MRI scan. The user does not need to understand electron band structure to use a touchscreen. In this sense, quantum physics is not a mystery to be solved before it is useful. It is a resource to be utilized even while it remains partially opaque. We are approaching a point in history where the quantum nature of technology is becoming more direct, less mediated. In the past, quantum effects were buried deep within devices, transistors operating in silicon, photons guided through glass fibers. But now, with quantum computers, sensors, and communication systems, the quantum state is no longer just a substrate. It is the data itself. We are beginning to manipulate entangled qubits, monitor decoherence, and transmit information encoded in non-classical states of light. We are no longer simply building atop quantum mechanics. We are working inside it. This shift comes with both technical challenges and conceptual adjustments. Working with quantum systems requires abandoning some of our most deeply held intuitions about how the world works. In classical computation, copying data is trivial. In quantum information, the no-cloning theorem forbids perfect duplication. In classical logic, knowledge is deterministic. In quantum systems, measurement changes the thing being measured. Even identity becomes murky. Two electrons are indistinguishable in a way that no two classical objects ever could be. They are not just similar. They are fundamentally the same under the rules of quantum field theory. As quantum technologies become more integrated into society, new forms of literacy may emerge. Already, students and professionals across disciplines are being introduced to quantum concepts once reserved for physicists. Understanding entanglement, coherence, and uncertainty may soon be as important to the general population as understanding electricity was in the early 20th century. And just as the electrification of society changed industry, infrastructure, and imagination, so too will quantum integration reshape how we think about computation, measurement, and even communication. There are, of course, limits. Quantum systems are exquisitely sensitive. Decoherence, the process by which quantum systems lose their quantum behavior due to environmental interactions, remains a central obstacle. Quantum computers require extreme isolation, often achievable only with expensive and bulky equipment. Quantum communication requires new infrastructure, and quantum sensors must contend with background noise and technical noise alike. These limitations are not insurmountable, but they temper the pace of adoption. Nevertheless, the trajectory is clear. Increasingly, the most advanced tools in science and engineering are those that exploit quantum effects. They allow us to simulate molecules, image individual proteins, detect gravitational anomalies, and synchronize clocks to such accuracy that even general relativity becomes relevant at everyday altitudes. These applications are not futuristic. They exist today in labs, in satellites, and in niche industries. Their diffusion into daily life is a matter of engineering scale, not scientific uncertainty. It is easy to think of quantum mechanics as something removed from ordinary experience. And indeed, the direct manifestations of quantum behavior, superposition, entanglement, tunneling, do not appear at macroscopic scales. They are washed out by decoherence and overwhelmed by classical interactions. But just because these effects are invisible does not mean they are absent. Every cell in your body is made of atoms that obey quantum rules. Every nerve impulse depends on ions crossing membranes through channels structured by quantum chemistry. Every breath you take carries oxygen molecules whose absorption spectra are shaped by quantized energy levels. You are quantum through and through. Perhaps the most profound way to live with quantum mechanics is not to seek comfort in certainty, but to embrace the richness of what it reveals. That reality is layered, not fixed. That the classical world emerges from the quantum, not as an illusion, but as a statistical approximation. That the universe is not deterministic in the way once imagined, but governed by amplitudes and probabilities, real, measurable, and deeply structured. Quantum theory teaches us that the act of observing is not passive, it changes the system. This may be true not only in physics, but in how we engage with the world. That to measure, to ask, to probe is also to influence. That knowledge is participatory. That our understanding is woven into the fabric of what we study. And so, living with quantum is not merely a technical condition. It is a philosophical posture. It is a recognition that beneath the smooth surfaces of the familiar lies a reality that is granular, indeterminate, and deeply interconnected. That certainty is useful, but not absolute. That logic is powerful, but not universal. That existence, at its smallest scale, resists simplification. Perhaps in those quiet moments, when you switch off your screen or put down your device, you might remember that what powers your tools, what underlies your data, what shapes your knowledge, is the dance of particles and fields in a world where rules are written in probabilities. That light flickers from quantized transitions. That time is marked by atomic resonance. That information, at its root, cannot be copied without cost. You are not a distant observer of this world. You are an emergent structure within it, patterned by its laws, animated by its fluctuations, composed of its smallest mysteries. The quantum is not somewhere else. It is here always. Thanks for spending this quiet time with me, friend. If you're still awake, there's another journey waiting for you. If not, let your thoughts drift. Good night and sweet dreams among the stars.